How do we dispose of nuclear waste? And what is the financial cost of nuclear electricity? So we talk about radiation. It's radioactive waste. That'll give you a lot of room at a party. Well, radiation comes in two parts. Electromagnetic waves, which their energy depends on the wavelength or the frequency. This is different wavelengths of light. So we know about visible light. The longer wavelengths, infrared, microwaves, and radio waves, are much lower energy, much lower frequency. But the higher frequency waves can ionize molecules, can cause mutations, which brings cancer and other kinds of damage. Ultraviolet, X-rays are even higher energy, gamma rays are even higher energy. So this electromagnetic radiation is one part of radiation, and the other is particles, such as alpha particles, which are helium nuclei, beta particles, which are electrons that are spit out by a nucleus, neutrons, which are neutral. These different kinds of radiation have different penetration depths. So for instance, alpha and beta particles are no big deal, but gamma rays and neutrons require lead or 10 feet of concrete to protect you. And so we have this radioactive nuclear waste that's it's quite dangerous. What do we do with it? Well, first it has to cool down. Remember the delay neutrons that the radioactive material is making. It's still physically hot. So it sits in a cooling bath for a period of time. Then we can take it out and keep it on dry land. One of the ways to prevent it from falling apart or getting lost is to vitrify it. That means to put it into a glass. So here you see the nuclear waste has been vitrified and is being kept as a solid. So where are we going to keep it then? It will certainly pile up, and there's a safety concern, there's a security concern for proliferation. How about if we kept it all in the same place? For instance, the proposed Yucca Mountain repository. Huge amount of research has been done on this to make sure it's reasonably safe for us to dispose of it there. We know about the geology. It's very dry. We study the technology. We're not just dumping it down in a hole. It will be built in a facility. We study the materials so it lasts long and keeps the nuclear waste contained. And we study the radioactive decay. Now you look at this graph and you say, what the hell am I looking at? So what does it mean to radioactively decay? Every time a radioactive material ages one half-life, half of the material is gone. And so the radioactivity decreases by a factor of 2. And so we can see after you undergo 8 half-lives, you've lost a good portion of your material. So for instance, if I graph the radioactivity of a substance over time, I can see it decrease exponentially. This is a substance that has a 10-year half-life. That means every 10 years, half of the material disintegrates. So after 10 years, we only have half as much. After 20 years, we only have a quarter. After 30 years, we only have an eighth. And then you say, well, what about down here? I mean, we need to have almost all of it gone. So we want to graph this on a log graph so we get some more detail here. And we can see that after 70 years, we have only about 100th as much radioactivity as before. But we have to wait much longer if we want almost all the radioactivity to be gone. So we would graph this on a log-log graph. And so now we can take it right out to 1,000 years. And we can see if you're willing to wait 1,000 years, or not even 1,000 years, you're only going to have 1 times 10 to the negative 21 of your original radioactivity. Okay, that's pretty good considering there's only 6 times 10 to the 23rd atoms in a mole. And so this is the shape we're going to see when we look at exponential decay on a log-log graph. And so this is what we see. These are all the different radioisotopes, and we see that they exhibit this behavior. But they often turn into something else that has a longer half-life. This is the total amount of radioactivity when you add all of these up together. And so this is all of the radioactive decay going on in the material graphed over time. Let's go up to years. So this is 1,000 years. So we see after 1,000 years, the radioactivity drops by about 100,000, 5 orders of magnitude. We understand the longer we wait, the safer the nuclear waste is going to be. if it gets out. Well, how likely is it to get out? So then we do all of these computer models for the probability that one of our waste packages will fail. So this is the portion, this is a probability of a failure, and this is years. We see it's going to be very safe until we have about 30 or 40,000 years go by, and then these packages will likely break down. So what we see here is the probability of exposure, because we don't get any exposure in the short term because our packages won't fail. And by then, the radioactivity of the substances is pretty low. Here's a conglomeration of all of the different computer models that predict the amount of radioactive exposure, radiation exposure we might expect over time. The EPA ruled that whatever we built at Yucca Mountain had to have less than 50 millirems per year exposure for the first 10,000 years. However, this was challenged in court by an environmental group, and the court ruled that yes, 10,000 years was too short and it had to be extended to 1,000,000 years. And the EPA responded saying, okay, 1,000,000 years is fine, but we raise the median radiation exposures to 100 millirems per year. The thing is there are all kinds of technical uncertainties with this model, and also the regulatory uncertainty. And there's something else that strikes me very strange. We're quibbling over the safety of a nuclear repository 1,000,000 years in the future when there's very little attention being given to the safety of our planet over the next 100 years or even 50 years with respect to climate change and other pollution and resource exhaustion issues. This graph shows the amount of nuclear waste that needs to be stored in the United States as a function of the year. And what we see is the year 2012, this year, actually coincides with the Yucca Mountain capacity. So this means if Yucca Mountain existed today, it would be full. Now, it's worth being said that this is just the Yucca Mountain repository. In the Yucca Mountain area, there's room for many more repositories, and so there would be the capacity to store all our nuclear waste in the Yucca Mountain area. In any case, Yucca Mountain was closed down in 2008 by Barack Obama. And now this created quite a problem because all the nuclear facilities had been paying 1/10 of a cent per kilowatt hour to the government as compensation for future storage of nuclear waste, and now they don't have it. We can look at the cost of researching Yucca Mountain has reached $10 billion by 2009. So is nuclear electricity cheap? Okay, be very careful. So the quote I often see is that nuclear electricity in the United States presently costs 1.7 cents per kilowatt hour. Wow, that's half the price of coal. It's really, really cheap. Why is that? But then we look at this publication by Dan Kamen, and this is the life cycle costs of electricity averaged over the whole lifetime of the plant. And we can see it averages between 3 cents per kilowatt hour and 15 cents per kilowatt hour. Now this is the production cost. So this is actually more expensive than most natural gas facilities and more expensive than coal. And actually more expensive than some solar facilities. This is actually quite expensive. And the reason is because there are very high capital costs. The expense in a nuclear facility comes from building it. We have built no new facilities in many years in the United States. So therefore, most of the facilities are already paid off. Their mortgages are paid off, the expense is paid off, and the only costs are fuel and maintenance. So presently, if we look at the cost of producing electricity now with our present facilities, it's very low. But that doesn't mean, but throughout the life cycle of the nuclear plants, the electricity averaged out has been pretty expensive. And so what that means is if someone tells you nuclear is cheap and we should extend the life of Diablo by adding 4 new generators and having a 50-year lifespan and spend a lot of money, you might disagree because you're worried about Diablo being on an active geological fault, but you recognize 1.7 cents per kilowatt hour is the cost we'd be looking at. However, if someone told you that nuclear is inexpensive and therefore we should build a new plant with new capital costs, this person would be a bold-faced liar if they were quoting 1.7 cents per kilowatt hour. So there are about 110 nuclear facilities in the US, and with about a decade to construct and 60 years of usable lifetime, the capital costs projected in the future create significant risk to the investor. What if something changes? Then I'm stuck with all this money I've invested to build the nuclear reactor. Now it's possible that we'll be able to make them cheaper and faster if we have modular construction that they're trying out a lot in China right now, and if we can also streamline the certification process. And so what does it cost? It costs between $3 and $7 a watt to build a facility. This is much more expensive than solar cells, however, on par with a full solar system when you have to include all of the other hardware and the installation. So is solar cheaper than nuclear to build? Well, be careful, because you can only use solar about a third or a fourth of the time. It has a capacity factor of on the order of 30%. However, nuclear has higher operational costs and external costs, such as safety and national security. Additionally, you have to decommission a nuclear power plant, and that's very expensive because the whole facility itself is radioactive. We don't have a lot of data on this because there haven't been a lot of nuclear reactors decommissioned yet, but the first ones is proving to already be expensive. And subsidies. How do we subsidize nuclear facilities? There's one large subsidy from the government, and that is no insurance agency would ever insure a nuclear facility because it's just too risky. But the United States government has stepped in to give them insurance so that they can get a loan to build a facility. So this is a huge subsidy for the nuclear industry, without which it could not exist. This is on par with coal. For instance, if it weren't for the railroad, which the government built, coal facilities would never be able to exist. Scientific American has covered both the very first reactor since 1978 that's been approved. They make a point to say that this is probably the exception that proves the rule, and that you shouldn't expect that this is the beginning of a whole bunch of nuclear facilities being built. Scientific American also covered a lot of what happened in Fukushima. So to summarize this, and some of this is my own opinion, you don't need to share these opinions, but please know the issues. I don't find nuclear as dangerous as the certainty of the problems we're having with coal. Yet, there are a number of unsolved problems. One of them is nuclear waste. It's not likely we're going to run out of uranium. And the issue with plutonium is very important. We should understand plutonium does not exist naturally. It's chemically distinct and can be easily purified compared to uranium. Renewable energy may be cheaper. Understand the difference in once a mortgage is paid off, nuclear facilities are very inexpensive to run because the fuel is inexpensive, but they're very expensive to build, so their lifetime average costs are between 4 and 15 cents a kilowatt hour. Nuclear energy is not dispatchable, not in the United States, and so it won't help us support our building up of renewable energy such as wind and solar, because it has to be on all the time. And fusion is great, but it doesn't work, or if we could make it work, we couldn't afford it. Or for the price that it would cost to make it work, we'd never afford it.